In geometry, a diagonal is a line segment joining two vertices of a polygon or polyhedron, when those vertices are not on the same edge. Informally, any sloping line is called diagonal. The word diagonal derives from the ancient Greek delta iota alpha gamma omega nu iota omicron sigma diagonios. From angle to angle, it was used by both Strabo and Euclid to refer to a line connecting two vertices of a rhombus or cuboid, and later adopted into Latin as diagonus. In matrix algebra, a diagonal of a square matrix is a set of entries extending from one corner to the farthest corner. There are also other, non-mathematical uses. Non-mathematical uses. In engineering, a diagonal brace is a beam used to brace a rectangular structure to withstand strong forces pushing into it, although called a diagonal. Due to practical considerations, diagonal braces are often not connected to the corners of the rectangle. Diagonal pliers are wire-cutting pliers defined by the cutting edges of the jaws intersects the joint rivet at an angle or on a diagonal, hence the name. A diagonal lashing is a type of lashing used to bind spars or poles together applied so that the lashings cross over the poles at an angle. In association football, the diagonal system of control is the method referees and assistant referees use to position themselves in one of the four quadrants of the pitch. Polygons. As applied to a polygon, a diagonal is a line segment joining any two non-consecutive vertices. Therefore, a quadrilateral has two diagonals, joining opposite pairs of vertices. For any convex polygon, all the diagonals are inside the polygon, but for reentrant polygons, some diagonals are outside of the polygon. Any n-sided polygon, convex or concave, has all diagonals. As each vertex has diagonals to all other vertices except itself and the two adjacent vertices, or n-3 diagonals. Matrices. In the case of a square matrix, the main or principal diagonal is the diagonal line of entries running from the top left corner to the bottom right corner. For a matrix with row index specified by and column index specified by, these would be entries with. For example, the identity matrix can be defined as having entries of 1 on the main diagonal and zeros elsewhere. The top right to bottom left diagonal is sometimes described as the minor diagonal or anti-diagonal. The off-diagonal entries are those not on the main diagonal. A diagonal matrix is one whose off-diagonal entries are all 0. A super-diagonal entry is one that is directly above and to the right of the main diagonal. Just as diagonal entries are those with, the super-diagonal entries are those with. For example, the non-zero entries of the following matrix all lie in the super-diagonal. Likewise, a sub-diagonal entry is one that is directly below and to the left of the main diagonal, that is, an entry with. General matrix diagonals can be specified by an index measured relative to the main diagonal. The main diagonal has, the superdiagonal has, the subdiagonal has, and in general, the diagonal consists of the entries with. Geometry. By analogy, the subset of the Cartesian product x times x of any set x with itself, consisting of all pairs, is called the diagonal, and is the graph of the equality relation on x or equivalently the graph of the identity function from x to x. This plays an important part in geometry. For example, the fixed points of a mapping f from x to itself may be obtained by intersecting the graph of f with the diagonal. In geometric studies, the idea of intersecting the diagonal with itself is common, not directly, but by perturbing it within an equivalence class. This is related at a deep level with the Euler characteristic and the zeros of vector fields. For example, the circle S1 has Betti numbers chapter 1, 1, 0, 0, 0, and therefore Euler characteristic 0. A geometric way of expressing this is to look at the diagonal on the two torus SYX S1 and observe that it can move off itself by the small motion 2. In general, the intersection number of the graph of a function with the diagonal may be computed using homology via the Lefschetz fixed point theorem. The self-intersection of the diagonal is the special case of the identity function.